Hello and welcome back to a new discussion. Today I'm talking to Martin Savage regarding quantum simulation of fundamental particles and forces. We've had plenty of conversations on quantum simulation in the past, but this is the first one that directly addresses, let's say, the standard model and things that are associated with that. I hope you enjoyed. Would you mind giving an overview of the particular area of quantum simulation that we're addressing here? What are we specifically investigating in this paper to narrow the scope a little bit?
Yeah, so good question to start. A lot of the challenges that we have in simulating the structure and dynamics of matter at its heart, subatomic matter, is beyond the capabilities of classical computing. So even beyond exascale computing. So we can do many things with exascale computing, but if you want to look, for instance, at the structure of very dense matter, what happens to matter as you rapidly change it, how do neutrinos evolve in dense systems, what happens in the earliest moments of the universe, then one cannot address those really important deep questions with classical computing, and one is then pointed towards quite cleanly, as Feynman told us about in the early 1980s, towards quantum computing. Now, it's not obvious that we can answer all of these questions with quantum computing, but it's pretty clear that we can answer some of them. So this is a relatively new field of exploration. It really kicked off 5 or so years ago, and the progress has been dramatic, sort of in partnerships with the rapidly advancing quantum computing hardware, with quantum algorithms, and also from the fundamental physics point of view, understanding how we use these systems and softwares and algorithms to actually solve the problems. So this review is a sort of a snapshot of outlining what the important problems are, and where we are in our understanding about how we're going to address them.
Mhm.
One of the interesting features in this area is that the complex I, the square root of -1, is really fundamental to this field. This is the quantum mechanics is where the I is essential. So in classical systems, one can um, introduce an I to make the mathematics cleaner and much more simple. But here, it's really fundamental to the physical systems.
Mhm. And does that play a significant role also in the simulation capabilities of these systems? Is the fact that I is an integral component of these kind of systems something that gets in the way of classical simulation?
Yes, that's exactly right. So typically the classical computing has a hard time with finite density systems. So this is finite density or high density systems of fermions, and also real-time evolution. In both instances, the I is playing a central role in those problems.
Okay, so that's one core problem with classical simulation of these kind of systems. Is entanglement also one of the key problems? I would assume it is, but maybe it's not.
Yes, no, absolutely. So well, not all entanglement is challenging. So, for instance, stabilizer states or are entangled, but they can be handled with classical computing. On the other hand, states that are, say, generically entangled and have magic are the challenge for classical computing, and this is where quantum computing really makes an exponential advantage in those types of systems.
Mhm. Okay, maybe as a follow-up on the point of the I that we were speaking about before. So there's something I read in your paper called the sign problem
Yeah,
that we encounter in nuclear and high energy physics.
yeah.
I take it that this is somehow related to what we were discussing before. Would you mind shedding some more light on what that problem is and some of the background of it?
Sure, sure. Yeah, so you're absolutely right. And so a simple example that one can think about is if you have the complex phase, say e to the I phi. So if I
Mhm.
write e to the I phi as cosine phi plus I sine phi, then, for instance, if we want to integrate that around the circle, we know that for any integer in the exponent at zero, if it's e to the I zero, then it integrates to 2 pi. But so typically, integrating around the circle is what one has to do in adding together Feynman amplitudes in the path integral, for instance. But if you wanted to do that numerically through stochastic sampling of picking random angles over the 2 pi and then averaging that numerical sum, that's where sort of that's at the heart of the problem, because that's going to converge to zero in a statistical way, and the instances where that answer is exactly zero, it's going to approach it with square root of n, because you're adding a series of vectors, increasingly large numbers of vectors of unit length, in such a way that the sum and the limit as n goes to infinity is zero, but at any finite sampling is not zero. It's going to be some statistical distribution that's converging like 1 over root n. And so that is one of the things that's at the heart of the sign problem. This is central to quantum mechanics, and as I said before, it's sort of integral to the Feynman path integral.
Okay. I was discussing very recently, actually, someone else who was also looking into quantum simulation, and I think there are a couple of benefits that tend to pop up when we discuss about this. So the first one is just computational complexity, that there are some problems in classical simulation techniques that are not well suited necessarily for those kind of simulations, and then a quantum computer could speed that computation up. I think there's also the aspect that with quantum computers, there are some simulations that you can do more accurately because of the nature of the machine itself, that it's better aligned. Are there any? So, do you agree with that statement, or have I gotten that a bit wrong?
No, I mean, I think at the heart of what you said, that's right. We're not in a position right now to use any of the quantum devices to do something better than we can do with classical computing. But of course, we're all hoping, and I'm quite positive on this, that within a few years, one will be able to find these problems. One will identify and make progress in important problems where quantum computing surpasses what's possible with classical computing. Now, I think what you're alluding to with the nature of the devices is, can you map your problem onto a quantum system in the laboratory and let that system evolve forward, as opposed to a digital computing? Did I get that right?
Yes, that you would be able to somehow pick an arbitrary time point in your evolution, and I think get a more accurate representation of any measurable in the system. I'm not entirely sure what the caveat would be with classical systems, but I think that's at the heart of it, that there are some quantities in this evolution of the quantum system that you would not be able to predict, at least not as accurately with a classical device.
Okay. So I misunderstood your question a little bit to begin with, but so one of the things that we have a very hard time with in simulating these fundamental systems is time evolution. And effectively, one doesn't have the ability to time evolve systems that are important, for instance, in astrophysics, or to compare with experiment forward in time using classical computing, because of the sign problem. And so today, we don't have the ability to do that with a quantum computer either, but the expectation is that will happen in the near future. And so, sort of to demonstrate how dramatic that is, so we have questions, fundamental questions about the nature of matter in nuclear physics, where even a calculation with 100% error or 200% error would be useful information, because classically we have that little ability to compute these quantities, and they're important. Dynamical, you take matter and you slam it together in a collider and you ask what happens. Classical computing struggles. I mean, it can't do that time evolution, most of it. And so quantum computing is expected to do that, and it was shown, 20 years or so ago, that time evolution of a prepared state is something that's efficient for quantum computers. And so that's one of the main areas that people are pushing on now in this particular domain of fundamental particles and fundamental forces, is to bring up a simulation of time evolution of a quantum system to demonstrate that, in fact, quantum computers are more efficient than classical computers and for these types of things. That's a big focus right now. That's a big focus.
Maybe related to this, when it comes to time evolution, at least, is trotterization. So that's a technique, if I'm pronouncing it right, used in quantum computing
Yes.
to break up the time evolution of a system. Could
Yeah.
you give your view on sort of the rationale why that's being done? Also, maybe a very short
Yeah.
introduction to what it is and yeah, why it's important.
Okay. Yeah, sure. So if one gives you an initial state, or you prepare an initial quantum state in the laboratory, or you prepare it on your quantum computer, and you want to then evolve the system forward and ask questions in the future about what that system does, how does it thermalize, how does it relax, and so forth, then at the heart of that is applying a unitary operator called the time evolution operator. So
Mm.
in all textbooks, you'll see it as U, or U of t, or U of t comma t0. And so, one of the fortunate things in the area of standard model physics and fundamental physics is we know what the Hamiltonian is. Right? The standard model, at least of the standard model, we know exactly what the Hamiltonian is. And for us, the challenge is to go from the Hamiltonian into an evolution operator that you can then implement onto quantum device. So there's a couple of elements to that. One is mapping the problem, but pertaining to the question that you asked is, how do I take this unitary operator, the evolution operator, and construct it in terms of the fundamental operations that you can apply on the quantum computer, on the quantum device, and then evolve that system forward in time. And so typically the Hamiltonians that we're dealing with are sufficiently complicated that you cannot take this entire Hamiltonian and construct a unitary operator that you would apply to the system just in one go. Uh, in principle, one could, but it's highly inefficient. The dimensionality, the issue in group that you would need to determine all the angles for, just scales very poorly, and it's not practical to implement beyond a few qubits. And so what trotterization does for you is allows you to look at the Hamiltonian and the different terms in the Hamiltonian that you need to apply over some time interval, and then break it up into the terms. If you get lucky, they're all commuting. Typically, that's not the case. So these operators don't commute, and then break this into small subunits, a sequence of smaller unitaries that you actually can construct quantum circuits for and apply them sequentially. So there's an error associated with that trotterization. And I should also comment that in this process, one can control the errors. There's leading order trotter, there's second order, there's third order, and so forth. And there's actually an extensive literature on optimizing this type of decimation of the evolution operator. So, a big part of what we do is to understand how to group terms and construct the quantum circuits that one applies, for instance, in layers. So if one has a quantum register of qubits stacked vertically, then there's circuit elements that one applies to evolve the system forward by some small time step, and you sequentially build out layer and layer and layer to do the time evolution that you want. But there's a systematic error associated with that, which you then need to be able to fully quantify and then mitigate in some way, or just live with it if it's small enough. So, trotterization is
Sorry.
one way to. Oh, no, sorry.
Please go ahead.
I was going to say that trotterization is one way to do this. It turns out to be, in many of the instances, most of the instances we've looked at, trotterization is a good way to go forward. But of course, there are other ways. There are different ways of using the quantum architectures to do these things, but trotterization seems to be one of the preferred methods.
Mm-hmm. The question I was going to ask just before was, is it fair to think by means of analogy of this as trotterization being similar to Taylor expansion in a way? That you have, because you said you had a leading order trotterization and then smaller order ones. Is it fair to think of it in a similar manner, that you have this operator that you're trying to approximate by sub-operators, if you will, or a stack of operators? And it seems to me, based on your explanation, that you sort of have a leading order term followed by other terms that are less important.
Yeah, yes, that's right. It's a little bit. I would say conceptually it's the same. One has to go from A to B, and there's a well-defined function. The function's complicated, but you know that at time t equals 0, it's 1. And you know that for a very small time step, there is a systematic expansion in the time step that increasingly converges to the exact evolution over that time interval. So yes, this is sort of a complicated Taylor series expansion. Yeah.
Okay. Is the procedure for finding such a breakdown well understood? Like when it comes to minimizing the errors that arise as a consequence of this trotterization, I assume you could
Yeah.
do it in many ways. You could, yeah. Is that literature well worked out, or is that a very active field of investigation?
It's an active field of investigation. Nature is always giving us surprises. So from a formal point of view, if the sort of time step's small enough, then one has a very well-defined mathematical framework to that things converge to. There's been some interesting experimental observations, and in hindsight, it's obvious. But if you think about what you're actually doing by working with a finite time step, you're essentially implementing a slightly different Hamiltonian. So when you do this expansion, you have H1, H2, H3, H4, H5, for instance, and you're breaking that sum up into unitaries that are then sequentially applied. So you're effectively applying a different Hamiltonian that depends on the time
Mhm.
step. And so that means that there can be instances where, for instance, you go into a different phase if that time step's big enough. And so there's been experimental and numerical demonstrations over the last few years demonstrating that point. So, for instance, you can perform the first few trotter steps. Everything is sort of converging nicely as you'd expect, and then as the trotter step gets a little bit larger, then you go into a chaotic phase, and the system just rapidly devolves away from where it should be. So there's an interesting field of study or subfield of study in this area, understanding um, the implications of this finite decimation of the evolution operator. And from an
Mhm.
effective Hamiltonian point of view, there's a lot of interesting physics there.
Mhm. From an operational point of view, let's say, when you're trying to implement this and you're trying to preserve the highest degree of accuracy that you can,
Yeah.
what do you think is the most promising alternative between finding better ways of performing the trotterization and then still trying to maintain somehow longer time spans of evolution, or trying to break up the computation? Because I think that's also something that was mentioned in the paper. If you have, let's say, a time evolution, and correct me if I'm misquoting here, but if you have a time evolution that you could potentially break that up into smaller evolutions and try to sequentially compute what you're trying to evaluate.
Yeah, that's right. As I mentioned before, trotterization is one way to go forward, the sort of the traditional trotterization. But with quantum devices, you have other things at your disposal. So, for instance, um, so there's a nice algorithm called Q-drift, and so, for instance, one again has um, one has the trotterized sets of operators. For instance, you have your Hamiltonians, for instance, 1 to 5 or 1 to n. Um, and instead of applying these in a sequential way repeatedly, one can statistically sample over applications with a weight determined by, for instance, the norm of the Hamiltonian in the states nearby to where you're interested in. And so you then can work with a lighter weight quantum circuit at the expense of having a much larger number of uh, elements in your ensemble to run on the machine.
Mhm.
So for instance, with trotterization, one has the evolution operator. You break it up and you apply it every time in the same way, starting from your initial state to your final state. But with Q-drift, you actually statistically sample based on a weighting of what the different terms in the Hamiltonian look like or do on the stage nearby the one you're interested in, and statistically sample. And that has instances particularly more in quantum chemistry, my understanding, that has significant advantages. In the systems we've been looking at, we haven't seen an instance yet where um, that where Q-drift outperforms Trotterization, but the studies are still sort of in their infancy. But
Mhm.
but that's a sort of a fundamentally different way of implementing the time evolution that takes advantage, for instance, of a system that actually has fast throughput.
Okay, that's interesting. I can put that also in the description, like some links to that if people are interested.
Yeah, okay.
But then maybe let's have a look at some of the figures that you also have in the paper. I
Okay.
think if we just sort of start with this one to give sort of an overview, would you mind just explaining well, what we're looking at here?
Yeah, so this is a schematic of what the objectives, limitations, and mechanisms are for the problem at hand. So, as I mentioned earlier, we're in this really fortunate situation that we know what the Hamiltonian is determining the dynamics of the standard model particles. And so, there are things we don't know, like dark matter, dark energy. We don't know all the properties of neutrinos and so forth. But for the standard model particles, we know what the laws are, and these are these are particles that, for instance, if one thinks about strong interactions, quantum chromodynamics, the theory of the strong force, then these are particles, the quarks and the gluons, but they're actually confined at a scale roughly of 1 Fermi, or 10 to the minus 15 meters, into protons and neutrons and pions. And so one of the great advances of the 1970s was to understand or define the laws, which are actually very simple, determining their dynamics, but the manifestation in terms of protons, neutrons, and nuclear forces is complicated, and it's still something, is one of the things that we're pursuing with quantum simulation. We also know about the electroweak interactions. We know how neutrinos interact with electrons and quarks and so forth. And the discovery of the Higgs boson somewhat completed the standard model picture. Going back to what we started with, taking those laws and then trying to compute with them with classical computing, you can go only so far. So you can do things very well, some things, low energies, small systems, and so forth. But going to scale, tackling the problems in the early universe, such as predicting the matter-antimatter asymmetry, understanding where matter comes from, which is fundamental to scientists, physicists. Understanding how you collide particles together in the laboratory. So you take two high energy particles, collide them together, they explode into showers of other particles. Understanding that time evolution is something that we can't do with classical computing, but it's something that we should be able to do in the future with quantum computing. And similarly, understanding the structure of matter, for instance, at the core of neutron stars, or what happens to matter in the dynamics of a core collapse supernova, is also something that one can go quite significant distances with classically, but there's still aspects to that, important aspects where quantum computing is needed. So this diagram, if you like, is the from fundamental physics defined at the electroweak scale through to the physics of the astrophysical and the high energy collisions. And the pathway is through a combination of classical computing and quantum computing. At least that's what this diagram was intended to convey. Maybe you should
If
maybe
we
you should tell me what you took from this diagram. That might be useful.
Well, I think you covered it quite well. I just think the applications of this are quite interesting, or the areas, and the reason why we're not able to predict that more accurately right now. So I was just about to ask, as a follow-up on the high energy particle collisions, like if we're looking at CERN and these kind of places where we are doing high energy particle collisions right now,
Yeah,
and we're to some extent leveraging classical computing for that, or we're leveraging lots of classical computing, but we
yeah.
don't get the full picture from it. What is it that or well, if you know what it is that we're lacking when it comes to the understanding of those particle collisions, because we have a system that's quite limited in the amount of particles that are included in it, and we're smashing two of these together at very high energies, it's breaking up into potentially particle antiparticle pairs that I guess would create and annihilate that would add complexity. But and is it then the complexity that is the issue here? Like, what is it that about these collisions that we cannot model right now?
So classical computing can do a lot, right? I mean, it's taken us to where we are today in understanding what we see in high-energy collisions. It's allowed us to understand, for instance, strong interaction backgrounds to make discoveries like the Higgs boson and so forth. So
Mm.
classical computing is good. It's good at doing this. It is highly constrained by experiment itself as inputs in order to be able to be that good. Now, the thing it doesn't do is it doesn't track in a significant way quantum coherence, and it doesn't accommodate entanglement. And
Mm.
so that's one of the those are the limitations. There's been work done during the last 5 years. A group in high-energy physics at Berkeley uh, started this, and they showed in a very simple one-dimensional model, which was what one could do at the time. They took this model and they went through the procedures that one does, to compare with the experiment, and then they also put the same system on a quantum computer and ask, what's the same and what's different. And even in that very simple model, they were able to detect a difference between the procedures, and they were able to detect, in particular, the impact. You could actually see measurable imprint of quantum coherence in the process. So,
Mm.
so that pointed in the right direction as far as understanding, um, where to go and where to look. So, it's important to realize that, the classical computing is absolutely critical to this, and the quantum computing
Mm.
is going to add to this, right? So quantum computing is not going to do all of this by itself. It's going to be
Right.
embedded in a very large classical computing environment, and together that's going to improve the situation.
Mm. Good. I think we can move over to one of the more technical pictures. So I think the overview is clear. Also, some of the problems are clear, and some of the ways that we hope we can address these problems are also outlined. We have one figure here, which is under the section of moving, I think, into a, quantum computational formulation of these problems. Um, this one I would like to understand a little bit better. If you wouldn't mind describing what we're trying to illustrate by this grid and then these subfigures here.
Yeah, okay, very good. So if one wants to perform simulations, even classically, of quantum field theories, um, then what one is trying to do is to take an infinite volume space-time continuum of fields, right? So our fields are defined in infinite volume and in the continuum, and perform simulations of that on a finite computational device. So that means one has to go from a system with an infinite number of degrees of freedom to one with a finite number of degrees of freedom, while preserving the symmetries and in such a way that the result of the computation at the end of the day is close to and can be converged systematically to a prediction of the continuum and infinite volume system. And so there's many ways one can think about doing that. The most common way to break the system up is to take the space-time continuum and put it onto a grid of finite volume. So instead of having an infinite number of degrees of freedom with a space-time continuum and infinite volume, one goes down to a grid. It has a finite volume, and there's a finite spacing between points of space and time. Now, if one's looking, for instance, at a process at some particular energy scale, as long as the discretization in space and the discretization in time is smaller than that inverse energy scale and that inverse momentum scale, then one should be close to be able to predict the result of the infinite volumes continuum theory. And more than that, one should be able to extrapolate by performing a series of calculations with decreasing lattice spacing and combining them and extrapolating. One should be able to make a prediction with a well-defined error bar with a complete quantification of uncertainties of what the prediction what should be in the space-time continuum. So that's what this grid represents. This is just one way of breaking up space and time is into what's called a hypercubic grid. There are other methods that people that have been around for a long time. There's particularly interesting development in the last year, considering, and this came out of Randy Lewis's group at York, thinking about Trimond space-filling lattices, which only involve three connections between three links, as opposed to the connections here in three dimensions, three space-time dimensions of 6 links. So this is also a field that's evolving forward, is how do you actually break up the field in such a way to preserve the symmetries, to have controllable predictions. And what we've drawn here is the hypercubic lattice, which has been very successful for classical computing. And I should mention actually the work that we're talking about here is done with Zora Davuti, Christian Bauer, and Natalie Clough. I should have mentioned this at the very beginning. So
Okay, very good.
what you're looking at here is the breakup of space-time. And so we've just done here, for instance, space at one particular time slice. And then you have to think about how do you lay out the problem onto this grid. And for instance, in the theory describing the strong interactions, which is quarks and gluons, the quarks are assigned to live at the intersections of the lines, and the gauge field or the gluons provide the connection between the sites, so they live on the links. And the Hamiltonian can be constructed in such a way in terms of evaluations on the links and also evaluations of what's called a plaquette, where you multiply around a square. You can combine those things in such a way that in the continuum limit, as the lattice spacing goes to 0, you actually recover the correct Hamiltonian and observables. One of the differences here in classical computing with stochastic evaluation, well, let me put it another way. One of the things that we have to do here in addition in quantum computing that we don't have to do in classical computing is worry about errors, for instance, checking that the charges are conserved during the evolution. So there's checks to look for errors that one has to do when the links cross to make sure the charges add up appropriately.
Is that some form of error correction is that an error correction that you're describing now, or are you talking about something else?
Yeah, so it's yes, at the heart of it, it's an error correction. So there's constraints, there's the theories that we're looking to simulate, they're electromagnetism, and that's relatively easy, but there are also non-abelian theories where the charges are combined in quite non-trivial ways, and one has to check that how they combine in the right way. And that has to be implemented by hand in Hamiltonian simulations, whereas that's not the case in the classical simulations in Euclidean space. So in a non-ideal quantum computer, one's going to find errors that will change the values of, for instance, of the links, or change the values of the quarks on the sites, the occupations of the quarks on the sites. And so one has to go in and check for those sorts of errors. And this is really at very early stages now, but it is something that's going to be essential in going forward to make sure the results are correct.
Okay. And when we're talking about this grid, or the splitting up of our continuum into this grid, are we saying that it's equidistant in this case, or could we also have a grid where the lengths here vary? I mean, I guess depending on what kind of split you do, you could have varying lengths, but in a split like this, a hypercubic split, I believe you said it was.
Yes.
Are the grid sizes always the same?
They generally are, but they don't have to be. So one of the techniques used for classical simulations, where you're simulating the full 4-dimensional grid at the same time, one typically has all 4 directions have the same spacing between the sites. But if you're looking for, say, very excited states, as are important for a number of experimental programs, then you can have a much smaller lattice spacing in the time direction than in the space directions. And so maybe sometimes you also need to look at a high momentum process. One is free to actually also shrink in the in any of the spatial directions you like. So it's not a requirement to have them all the same size. Sometimes it's useful. It requires far more effort to tune, to understand the lattice spacings that you actually have if you have these. It's called anisotropic lattices, but it's doable and they have utility for some particular types of observables. It depends what you're
Okay.
chasing.
Uh-huh.
Yeah.
And maybe this is a stupid question. Yeah, sorry, go ahead.
No, carry on.
So maybe this is a stupid question, but we have this grid size of, let's say, equidistant grid size, and we're modeling the fields with this, or we're actually modeling a quantized version of it. So do we have discrete particles that we place, or subatomic particles that we place in this grid, or is this in a continuous way modeling a field where each, let's say, intersecting point contains a field value?
So you're asking a really good question, and this is getting to things that are still not settled in the sense that there's lots of exciting progress being made. But the question you're asking, how do you map your problem onto the grid? So it's fine to write down the space-time grid, but you have fields that sit on top of them, and how do you map your problem onto the system? And so one of there's no right answer at the moment. There's no mapping that's been defined to be better than any other mapping. So people are trying, and there's far more to go here. People are trying all the potential ideas that they can think of and inventing new ones as to how do you actually lay out your fields and particles onto these systems. So, for instance, the typical one that we have that's in this diagram is that quark occupations sit on the vertices. So, for instance, one could have a qubit that when it's spin down, a Jordan-Wigner mapping type qubit. So when it's, say, spin down, there's nothing there, and when this qubit spins up, points up, that would indicate that there's a red up type quark present. And so the wave function for the system, for this quantum system, will have some linear combinations of all of the sites, in particular occupation numbers on the Bloch sphere between 0 and 1, defining what the state of the field is at that particular instant. So that's one way to do it. One doesn't have to use a single qubit to denote occupied or unoccupied. One can think about mapping to qubits, for instance, where one maps the occupations of the different colors onto, for example, an 8-dimensional system. The gluons, you have the same freedom. So the gluons, one can work in this instance in the Kogut-Susskind basis, which is defined by the electric field, sort of counts the chromo-electric flux moving along the link. But one can also map in a different way where you're just sampling orientations of the gauge field. So these are conjugate variables. And the community is exploring all of these different types of mappings. At the moment, there's no right answer. And we just had a workshop here in Seattle that ended on Friday, 2-week workshop on pulses and qubits and quantum simulation, where this was constituted a fraction of the discussions, has had what are the appropriate degrees of freedom to map and how to map them onto different hardware.
Okay. The last part of this equation that I would like to, or this figure that I would like to understand a bit better, is just this sub-figure up here as well. So we have these different schematics with arrows pointing between them. What is this actually representing?
Right. So this is representing what happens in group space. So if we're thinking about electromagnetism, then for instance, one has electrons and positrons, and the wave function under a gauge transformation. So firstly, nature is invariant under local gauge transformations, which means that at each point in space-time, I can redefine the phase of the wave function. It's compensated by changes in the gauge field to leave all observables the same. That's one of the basic principles for establishing the Standard Model. So for
Mhm.
electromagnetism, this means one understands that electromagnetism corresponds to a U1 gauge theory, and there you have electric charges. So if I have an electron, then it's got charge -1. If I have two electrons, it's got charge -2. If I have three electrons, it's got charge -3, and so forth. And I ask, what is the total charge of a system when I put n electrons into a box? And it's -n. They just add numbers.
Mhm.
Now, in contrast to that, the electroweak sector is defined by an issue 2 non-abelian gauge symmetry acting on left-handed fields that's combined with a U1 gauge symmetry of hypercharge, and they undergo spontaneously breaking to give us electromagnetism at low energies. But the issue 2 part's a non-abelian gauge theory. And then the theory of the strong force is an issue 3 non-abelian gauge theory, and that has the quarks and the gauge fields of gluons. So if you ask if I have a quark here, then that has color charge, it transforms as a triplet, a 3, and issue 3 of color. Now, if I put another quark next to it, and I ask what is the color of that system, it's not 3 plus 3. They combine in a non-trivial way to give a 6, a representation that transforms a 6, and one that transforms in the anti-fundamental representation of a 3 bar.
Mhm.
So I have coherent superpositions of a 6 and a 3 bar. So that means that when I actually when I look at the evolution of so a wave function, for instance, when I act with the Hamiltonian, if I just act with it once and I'm acting on, for instance, a link with no flux, that will take me to a 3 or a 3 bar. But if I act on it again, then the jargon is 3 cross 3. That's a 6 plus a 3 bar. But if I'm acting on a 3 bar, 3 cross 3 bar gives me an 8 plus a 1. So that means I don't just get to add and a ladder go up and down in a straight line. I have these branch points, and generally for every time I act with a Hamiltonian, I can go in 3 different directions. And so hence
Okay.
that's why you see this connectivity in the rightmost element in that box.
Mhm.
So
Right.
issue two is more like U1. I get, for instance, if I do spin 1/2 cross spin 1/2, I can get a 0 or a 1. So I basically can go up and down. But in issue 3, then I actually have a two-dimensional surface that I can occupy.
Okay. And this information, so to speak, is then encoded in the Hamiltonian of the system, or where is the trace of which gauge theory we're considering?
Right. So the Standard Model has well defined the gauge group, for instance, of the strong interaction as issue 3. Uh,
Mhm.
and a large part of the experimental program of the 20th century and is ongoing was to uh, verify and basically identify the different types of quarks. So we know that there's 6 quarks, 6 flavors of quarks, and we know that they have 3 colors. And so the strong interaction part, at least as far as we've probed and are able to probe, is consistent with that theory. One expects there's probably physics at some higher scale that can lead to short distance, small corrections to that, but the big piece, the very big piece, is defined by the quarks and gluons interacting via issue 3, strong interaction Lagrange density of QCD.
Mhm.
Um, so that is specified. So that's given to you. And so the challenge in this particular area of quantum simulations of QCD is to understand how you actually take those degrees of freedom, do this decimation onto the grid, and then also there's another aspect of here that we haven't mentioned. The gluons, if you like, correspond to a result from a continuous 8-component phase, multiplying the wave function. And so there's continuous degrees of freedom that have to be included in the simulation, not just fermions. And so mapping those is non-trivial, and that's part of the discussions that are ongoing.
Mhm. Okay. We could dive into that, but I think in the interest of time, I also want to have a look at the final figure and some of the applications associated with this. So we have this one in the end, and maybe if we start looking at the top left part of this, if you would mind explaining what we're looking at there.
Yeah, sure. So this is work that we did in Seattle. So this was so if one wants to start simulating the gauge series, the non-abelian gauge series, or even the abelian gauge series, one has to build up and understand in great detail what happens to the simplest object and then build out, right? And so typically we spend a lot of time understanding simple small units, make sure we understand those in great detail, how they perform, and then we start putting them together to try and go to a much larger volume to do simulations on. So what you're looking at here is simulating just one plaquette of glue. So there's no quarks present. There's just one of these squares from the previous figure that has gluons on it. And we start the system in the trivial vacuum, so there's no gluons present at all, which is not the quantum vacuum. The quantum vacuum is non-trivial combination of occupations, but in the trivial vacuum, so you can imagine you just were able to start the universe, and in this case, the universe is one square, and you just set everything equal to 0, and then you did time evolution on top of that with the full Hamiltonian. And you ask, what happens? So what happens is that the quantum fluctuations then give rise to color flux, strong interaction flux, being populated on this square. So really, from a different perspective, you're starting in a particular state that's not an eigenstate of the Hamiltonian, and so the evolution then will project onto the eigenstates, evolve the eigenstates, and you'll see the energy in the electric field, in the chromoelectric field, become time dependent. And so that's what you're seeing here. You're asking how much energy is there in the chromoelectric field as a function of time, starting from the trivial vacuum. And so this was work that you can do this, you can solve this problem classically on your laptop in no time. It's a very easy problem. It's small. You can choose. There's a large range of couplings where this is just an easy problem for classical computing. But putting this onto a quantum computer, this was stretching the limits of what quantum computers could do a few years ago. So we did the first calculation around 2018, 2019, and this was at the limits of what the best quantum computers at the time could do. So either the superconducting systems of IBM or the trapped ion systems of IonQ, for instance. And so here's the result that you find on this particular calculation was done, I think, 2.5, 3 years ago. And the upper points correspond to the results obtained from the quantum computer itself without taking into account the errors and the decoherence of the quantum computer. But there's sophisticated error mitigation techniques that have been developed. IBM's done a lot of the development. Other groups have done development. And when you combine all of the error mitigation techniques together and bring it to bear on this problem, one goes from the points on that upper curve to the results with the uncertainties that you see oscillating just above 0. And the solid curve there it corresponds to what you expect, and that's the result of classical computing. So this was to demonstrate that you could actually do time evolution on a plaquette over many cycles with good and obtain results from modern quantum computers that actually reproduce what you expect them to reproduce on this system. So that's what their figure's about. Yeah.
Am I correct in understanding that the line of 0 here is the one you would expect? Yeah. Okay.
It's the line through the blue points is what you expect.
Okay. It's the dashed line that goes through them.
Yeah, that's right.
Okay.
So what comes off the quantum computer, it gets it right within errors.
Yeah.
Over many trotter steps.
Yeah. Okay. Cool. And then the associated circuit that somehow goes along with this is to some extent represented down here as well. I don't
Yeah,
know what we're
yeah,
seeing there exactly.
yeah. So that's a cartoon. So that's a cartoon of the quantum circuits that were applied. Um,
Yeah.
so 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 if so, this is a detail from the previous figure. So if you look at how you actually do the layout in the Kogut, Susskind, Hamiltonian, this particular formulation that we've been using, is you have a essentially a dumbbell. So you have a contribution to you have a state in a Hilbert space on the left. You have a state in the Hilbert space on the right, and these are connected to each other because they have this, they transform the same representation of issue three. Um, but you have this gauge freedom in each on the left-hand side and right-hand side that are completely independent. So one of the formulations that you can do is to um, analytically or classically perform the integrations over the left-handed side and the right-handed side, and that leaves an effective Hamiltonian, but it depends on what the flux coming into that corner looks like. Well, but you can think about it as having control qubits, asking what is the flux around it, and that dictates what the amplitudes are for the transitions within the plaquette itself, within the square.
Mhm.
So this circuit is a representation of that type of circuitry. So you basically
Okay.
have multiple controls. You ask, well, there's an 8 coming in here, there's a 10 over here, 27, and a 3, and that constrains the action of the Hamiltonian on those particular elements of the wave function.
Mhm. Just one tangent to this from a separate discussion I had. I don't know if you're familiar with light front quantization, if you heard that
Yes.
before. Is that
Yeah.
something that's being used also in combination with this kind of like grid introduction? Because I guess the difference if you try to do something like that was you would create the grid differently when we tried to implement this in a quantum computer.
Yeah.
I'm just asking the question because it seems like for maybe these kind of applications, but also like relativistic collisions like this, there could be
Yeah.
utility in mapping it onto something like that.
So that's exactly right. So the discussions that we've been talking about are something you would do. Basically, you pick a particular hypersurface, if you like. You pick a particular time, that time slice, you have your space, and you set up your problem. But there is benefit to thinking about light front quantization, where one is explicitly um, uh, your reference frame is explicitly defined by the light cone massless particle, and you have transverse directions. And so you still have transverse directions that you need to discretize and evaluate non-perturbatively, but it changes how you map the problem. And it's been known for a long time, since the 70s and the work by Ken Wilson and others, the potential advantages of working with light cone for particular types of observables. And so there are
Mhm.
people that are pursuing quantum simulations using light front coordinates as well.
Okay.
So this is
Yeah.
another one of the mappings that people are looking at in order to address these problems. Yeah.
Okay. Understood. Very good. We only have a few minutes left, and we didn't really cover everything in the paper so far. So rather than trying to step through the last subfigures that we have here, I would just ask if there are any interesting areas of application for this kind of technology that we haven't yet mentioned that you would like to raise.
Okay, great question. So, so, so that's a very, very big question.
Yes.
So a lot of so if you look at what happened in the 1970s, 80s, and 90s for classical computing, so there was a big drive in high energy physics in particular that then branched into nuclear physics of solving QCD. It's important that we understand what happens to strongly interacting, highly correlated matter under a range of
Mhm.
conditions. It's really important. And so that setting up a hypercubic grid to do the simulations, at least of sets of observables, that led to us the development through co-design of quantum computers, of classical computers, the QCD-OC and the QCD-SP collaboration of Brookhaven, Ricken, and Columbia. And these machines were designed to solve this problem. They were optimally configured on the hardware side to solve this problem. And ultimately, that led actually to the IBM's Blue Gene series, the LP and Q classical computers, because they have the four-dimensional hypercubic or four-dimensional toroidal communication fabric. They're very efficient for solving lattice quantum field theory problems. So the same is happening here, right? Everybody, the people in our community and the physics community collaborating with people in the quantum hardware, quantum algorithms, quantum software, developers to attempt to solve these problems, but it's mutually beneficial to the advancing the hardware as well and advancing the algorithms. So the co-design is not just be able to solve these problems, but it has impact more broadly on the design of quantum computers and algorithms.
Right.
Does that
Okay.
get to what you were asking?
Yes, exactly. If
Yeah.
there is anything else that you would like to just say to the community or people listening before we close the interview, you're more than free to do so. Otherwise, we'll, I think, end it here.
Okay. I think we're fine. I think we've covered things. So
Awesome.
thank you.
Then thank you very much, Martin, for taking the time.
Yeah, my pleasure. Thank you very much.